Thanks. I will begin. Dear Heavenly Father, we thank you for this day again. Lord, I thank you for the students. Just pray you to bless our work today. Help us to understand as much as we can in the time we have about L'Hopital's rule, Lord. In your name I pray. Amen. So I'll give you guys back your test at the end of class as to not distract you. I'll just tell you a couple things about tests while I'm on the topic. Number one, like you guys, problem 2, a lot of you, like maybe half the class tried to integrate by parts and somehow you got something. That's not legitimate. Like you can't. When you integrate by parts on this, it goes back to where it starts and it tells you nothing. It tells you that this quantity is a constant, which it is, but you know, that's not helpful. So to do that integration, you really just need to go back to the definition of Cauchy, and that's why it's on page 1, and it's just an elementary integral. But anyway, the other one I was surprised by, that cosine 3x, cosine 5x problem. You know, I don't know, maybe 5 or 6 of you tried to integrate by parts. There, if you'd done it correctly, you would have gotten full credit. Unfortunately, there's kind of just a hodgepodge of errors that you guys made along the way. If you've been careful there, actually integration by parts twice on that problem will solve it. I did not know that. It should have occurred to me, but I didn't even think of it. But you're right, it does loop back, but it loops back with a rather unpleasant and unwieldy fraction, and no one really hacked the arithmetic there correctly, so everybody lost something who tried to do integration by parts, I think. In my solution that I'm going to post, I have the integration by parts solution at the very end, as well as this thing. And then the solution I intended, of course, was just for use trig identity to convert it to a sum of trig functions you can integrate. By and large, I think you guys are doing pretty well. Not everybody's where they want to be yet, but you know, if you made more than about a 50% on this test, there's good hope for you passing. If you made less than 50%, you know, statistically speaking, something needs to change. What that is, I don't know, but anyway, I will post the solution and give you back the test today. So that's upcoming events. So L'Hopital's rule. First of all, I need to remind myself how to spell it. L-H-O-P-I-T-A-L. I sometimes add an S to this because it's more fun. Like sometimes I stick an S in there because then it's the hospital rule, which is more fun. But L'Hopital's rule. So first of all, before I get carried away in this, how many of you have already seen L'Hopital's rule in their previous calculus existence? Who has never seen L'Hopital's rule before? Couple. Okay. Yeah, to me it's very odd that it's here, but this is where it is in the book, so it's where we cover it. But a lot of people have seen it in Calculus 1, even here maybe. I've covered it in Calculus 1 before here. But anyway, what's it about? L'Hopital's rule says that if we have type 0 over 0 or infinity over infinity, then we can calculate the limit of f over g is equal to, by L'Hopital's rule, the limit of f prime over g prime. Right? Now I'm being a little bit vague here. See, because L'Hopital's rule applies to all kinds of different sorts of limits. It applies to limit as x goes to like plus or minus infinity. All right? You know, this is a case where L'Hopital's rule applies. But you could also have x going to a, right? You could even have a left or a right limit. These are all your favorite kinds of limits have a L'Hopital's rule. So L'Hopital's rule is available for any of our limiting processes that we're interested in. Limits, right, left limits at finite points, limits at plus or minus infinity, all of these L'Hopital's rule available for us to use, provided one thing. We need to have type 0 over 0 or type infinity over infinity. Let me show you what happens if you don't pay attention to that. Example 1. Limit x goes to 1 of x squared plus 1 all right, over 2x squared plus 3, all right? Apply L'Hopital's rule incorrectly, and if we differentiate the top, what do we get? 2x. We differentiate the bottom, we get 4x. Yeah. And so the x's cancel, and we get a half, right? But it would be just my luck for the answer to actually be a half. But in fact, it's not, right? This, you don't need, this is not, in fact, not an indeterminate form, right? Right? As x goes to 1, is that expression defined? I mean, can you plug 1 into that without violating rules of arithmetic? Absolutely you can, right? 1 squared plus 1 over 2 times 1 squared plus 3 is 2 over 5. Yeah. Of course, 2/5 is not 1/2. Right? So L'Hopital's rule does not always apply. You must meet the condition. You have to start with 0 over 0 or infinity over infinity in order to apply L'Hopital's rule to a quotient. Yeah.
Are we denoting L'Hopital's rule with, or the application thereof with that?
Indeedly doodly. This script L is what I will use to denote L'Hopital's rule. Your alternative would be to write an equals and then put a parenthetical comment on the side that says L'Hopital's rule type whatever. Without this, right, be applying L'Hopital's rule to type whatever. I insist that you denote also, you must somehow indicate that you're using L'Hopital's rule and which type you're using it to in the interest of full disclosure. Okay, so let me show you an example which is more fun. Example 2. Here's a good one. Limit as x goes to 0 of sine x over x. All right. Now, this is type 0 over 0. See, because the numerator limits to 0, the denominator limits to 0 as x goes to 0. So this is type 0 over 0. Yeah.
Isn't that equal to 1 now?
It is. Now, how do you know that?
There's a proof for it.
Very good. Right. There is a proof. And in fact, what I'm writing is totally circular because in order to do what I'm doing, I need to know the derivative of sine is cosine. Right? Now, the derivative of x being 1 is that I get. But you're right. There's a certain hypocrisy in this example of what I'm doing because in order to prove the derivative of sine is cosine, in fact, I need to know that the limit as h goes to 0 of sine h over h is 1. So yeah, you got me. But it's still a nice example of L'Hopital's rule because this is, of course, cosine of 0 over 1, also known as 1. So my point to you would be if you didn't remember that, you can derive it now with L'Hopital's rule, which is pretty nice. Example 3. I'll keep with these easy examples for a bit here. If we take the limit as x goes to infinity of x, e to the x, what do we get? I'm not just doing L'Hopital examples here. Yep. Go for it. What do you think?
I was going to say, what's wrong? My answer's wrong. But I was going to say infinity because there's...
No, you stick to your guns. I mean, you're right. This is not a L'Hopital's problem. We have x, which is going to infinity. We have e to the x, which is also going to the infinity. Something that's going to be huge times something else that's going to be huge is, in fact, huge. Yes, thank you. So yes. Sorry. Yeah, it's infinity. Now, of course, in this case, it does not exist, right? But so does not exist is a big category of limits. When we say does not exist, we mean does not exist as a real number. A philosopher might argue with you that if you're calculating the limit, in some sense it exists, at least in the realm of ideas that you can discuss, right? I mean, how can you discuss a limit which doesn't exist if it doesn't exist? So when we say does not exist, we're talking about real numbers. Infinity is not a real number. this limit does not exist. That infinity is better than does not exist because it's more descriptive, right? You write a limit, it's infinity. You're saying that that limit, the function that you're taking the limit of, grows without bound in that context, right? If I just say does not exist, here's an example, one of those. Limit x goes to infinity sine x, right? This does not exist. Because what happens to sine as x goes to infinity? It oscillates, right? So you could improve on my answer, and you could say this does not exist due to oscillation. That would be an even better description of why the limit doesn't exist. I'm supposed to be talking about L'Hopital's rule. Let me get back to it. Example 5. How about this? Limit as x goes to minus infinity of x e to the x. See, now we got something a little bit different. So what's going on now?
It's going to 0, right?
Well, one of them's going to 0, right? The e to the x is going to 0, but what's happening to the x? It's going to minus infinity, right? So we have minus infinity times 0. What happens? Which wins? The x or the e to the x? Right? If the x wins, the limit should be a very large negative number, or the limit's minus infinity, right? I should say, yeah.
Is that the stuff where you like take the integral and then you like separate it?
Oh, no. You're thinking too hard. This is a welcome, like, I know we had that test yesterday, a certain unpleasantness, but this is relaxing. Like, there's no integration here. It's just limit, derivatives. What's that?
Is that a thing though that I was saying?
I think you're thinking about maybe like comparison test or integral test, maybe. Maybe. This is type infinity times 0. See, we don't care about sign. I mean, you might say it's type minus infinity times 0. We don't care about that sign. Like over here, you could have infinity over minus infinity. It's still counted as infinity over infinity, all right? But this is type infinity times 0. I cannot apply L'Hopital's rule to that. So what do I have to do? I don't just say it's 0. I don't just say it's infinity. This is an indeterminate form. That means without further calculation, we can't be sure what it is. Indeterminate form, yeah. So here's what we do. We do a little bit of algebra. We make it into something we want. So this is x over e to the minus x. Right? So I just made an algebra step, but that algebra step is to move the 0 from the numerator to the denominator. And when you move a 0 from the numerator to the denominator, you turn it into an infinity, essentially. So this, you see through this algebra step, this now is what? This is type infinity over infinity. See, notice that e to the minus x goes to infinity as x goes to minus infinity, because we got minus and minus, which gives us a plus. Yeah.
Why isn't it not 0 if it goes to infinity in the bottom?
Well, we don't know, because this is infinity upstairs as well. It's infinity over infinity. It's an indeterminate form.
Even if there's a power, or if there's an exponent, you can't say that that infinity would therefore be bigger than the infinity on top because it's exponential.
I think you're right, but we'd like to derive that. Yeah. I mean, you're jumping to the answer, which is not bad, but let's understand why that's true in view of L'Hopital's rule, right? Infinity over infinity. Limit. What's that?
Because it's a 1 up there, right?
A 1?
Yeah, like,
Oh, x to the, yeah, I mean, yeah. Well, I'll say more in just a second here, but let me finish this example. So there's one, I apply L'Hopital's rule, differentiate the top, differentiate the bottom. I am not doing the quotient rule. Some of you guys, you get further into this, you forget what you're doing, and then all of a sudden you're differentiating the quotient. No! L'Hopital's rule is kinder than that. It says differentiate the numerator and you differentiate the denominator separately. It's not differentiation of the whole thing. It's the quotient, one at a time. Now what happens? Now I'm on board with you. See, now this is basically 1 over infinity is the type that we have now, okay? That's the pattern. Top goes to 1. The denominator goes to e to the minus minus infinity, which is e to the infinity. E to the infinity is essentially something huge. So we've got 1 over something huge, which is not an indeterminate form. This is what? 0, right? Yep.
So could we have just plugged negative infinity into e to the x, and that sign would have flipped to the bottom immediately?
E to the negative.
Because you say we don't care about the sign, but I feel like that's what the sign would have done.
I'm
Like you just end up doing the same thing.
What do you mean plug negative infinity into e to the x?
Into e to the x, be e to the negative infinity, which is x over.
But I mean, you'd have to. I mean, how do you calculate minus infinity e to the minus infinity? See, we don't know what to do with that.
Well, I mean that minus implies that there's nothing.
That is the intuition behind making that algebra step. Yeah.
You just
We have to show our work. Yeah. So here, let's look at another one which is less weird. How about this? We have limit as x goes to infinity, right, of x squared e to the minus x. So again, I'm facing something. This is infinity times 0 is the initial type, right? That's type infinity times 0, right? Because if x goes to infinity, x squared goes to infinity. On the other hand, e to the minus x goes to 0 as x goes to infinity. Make sense so far? I cannot apply L'Hopital's rule to that, right? So I need to convert it to a quotient. And I think the way to do, I mean, you got choices, right? Here, I'll show you both choices. The one choice would be to do this. X squared over e to the x. That's the right choice. Or you could do, leave e to the minus x up there, and put 1 over x squared down here. I mean, that's another choice. So the left hand, I've recast it as a type infinity over infinity, right? Whereas the right hand, this is type 0 over 0. So great. I mean, I can apply L'Hopital's rule to it. And when I do, what happens? Nothing particularly interesting. It got even worse. So this is a wild goose chase, right? This is not going to work. It's important that I show you this because as you're working homework, you might take this path and it doesn't work, right? Then you got to think, uh-oh, I should go back to where I made my algebra step and try something else like this. And this is going to be better, right? Because I apply L'Hopital's rule. I'm sorry. I'm supposed to write 0 over 0 here. Anyway, type infinity over infinity. Limit is x. Do I need to write the limits? Yeah, probably to start with. There are other ways of writing limits without explicitly writing limits, but they require the use of grammar and such. So the easiest thing for me to tell you to make sure that you got correct presentation is to write limits where you should have them, right? Yep. Oh, you just, okay. So the first application of L'Hopital's rule didn't solve our problem, right? Because this is still infinity over infinity. So again, and we got 2 over e to the x, right? Now that's type 2 over 0, excuse me, 2 over infinity, right? E to the x gets huge as x goes to infinity, so this is just 0. Yeah.
Like, I'm thinking about this in 2 different ways. I was thinking like that x is an infinity, it would be e to the 0, which would be 1, and thus the limit would equal 2. Or why doesn't it just, if it does equal 0, and if it is getting
I don't understand. What did you say?
So like if we let that x equal infinity, so it's getting infinitely smaller since it's
Well, I don't know what you say x equals to infinity. I don't really know what that
or like
means.
substitute it in like because
We really can't do that is the point.
you just have to
No, you notice I'm being very careful to always say type 0 over 0, type infinity times 0, type 1 over infinity, type infinity over infinity, type infinity times 0, type 0 over 0. I've made a point of writing type. The reason I'm doing that is I want to emphasize to you, I'm not actually plugging in the limit point. I'm looking at the pattern of the limiting functions. That's what we have to do. See, because I don't know what to do with infinity times e to the minus infinity versus infinity squared. Like, what's the arithmetic of this? How do I manipulate those expressions? There are people who can. They're called physicists, but they have this thing called physical intuition. I'm not really. But there's all kinds of black magic that they do that has to do with physics that you can use infinity. No, we must write. You know, guys, here's some things I could write about infinity which would be unambiguous. Maybe this is helpful. E to the infinity, infinity. E to the minus infinity, 0, right? 1 over 0, infinity. But that's actually, I got to put some quotes on that because this gets me into trouble. See, because 1 over x, it goes to infinity, and 1 over x goes to minus infinity, depending on which side you are on, right? As x goes to 0 from the right versus as x goes to 0 from the left. See, so even something like this, I can't even really commit to infinity unless I'm willing to commit to plus and minus infinity being the same infinity. So these are the kinds of things you have to sign up for if you're going to start doing arithmetic with infinity. It's really dangerous. Yeah.
But for the example, 2x over e to the x, when that became 2 over e to the x, are you saying that x, 2 times infinity can just be stated as 2?
I'm saying that we're looking at a limit where we have 2 in the numerator and we have e to the x in the denominator. So as x goes to infinity, this becomes very large, which means this fraction becomes arbitrarily small. So the answer is 0. It's an arbitrarily small positive number, so it's 0.
Yeah, but from the step above that, how did you get from 2x to just 2?
Oh, differentiating, L'Hopital's rule. I applied L'Hopital's
So
rule.
you applied it a second time, okay.
Now what you were saying though, Darius, is it?
yeah, I guess.
You have something that's absolutely right. Like in a battle of exponentials versus polynomials, the exponential is going to win, right? So like once you see that there's an e to the x downstairs, this could be x to the 20th. This would just require like 20 applications of L'Hopital's rule. We know it's going to go to 0. On the flip side, if we had, you know, if we put our x squared downstairs, right? Something like this. And maybe I should make this into a, here I'll make this into an e to the x, just to compare this thing. What's going to happen there? I mean, it's going to go to infinity, but we can show that without ambiguity. This, at the moment, you can't say that, I mean, you shouldn't, I'm happy if you have the intuition that you know that that goes to infinity. That's great. That's actually what we're after at the end of the day. But I also want you to be able to show me that that's true with L'Hopital's rule. And so to prove that here, I have to do this. So this is type infinity over infinity, right? And so here, let me make it more exciting. 2x there. Now we'll feel like we're actually doing something. So 2 e to the 2x, right? And then one more application of L'Hopital's rule. We've got 4 e to the 2x over 2, right? And this thing, there's no ambiguity here, right? we're looking at something which grows without bound divided by 2. I mean, this is clearly, by precalculus, essentially infinity. I mean, the end stage here, there are really a couple different arguments I'm thinking about. The one is, I know what e to the x looks like, right? Or I know what natural log looks like. I know what algebraic functions look like. I understand their graphs. So I know what their long-term behavior is, right? And that allows me to say infinity or minus infinity as appropriate. The other idea is just, I don't know the graph, but I can look at the expression and I can just, I mean, I don't think about this graphically. I could, but I don't. I think about this as I've got 2 divided by something that's getting huge, right? So this was going to give me a limit of 0. Yeah? Oh, okay. That's fine. Right. I don't think I've done any terribly difficult examples just yet. Let me try to pick something that's a little bit more annoying from the text. For example, number 39. Here we face the dreaded limit. Actually, I don't know if it's that dreaded. We have limit as x goes to 0 of inverse tangent over sine x. So, sidebar. Note, inverse tangent of 0 equals to 0, and sine of 0 equals to 0. Hence, limit above is type what? 0 over 0. I cannot actually evaluate it at 0, right? Because I'd have 0 over 0, which is undefined, and yet we can calculate the limit of it. That's the subtle thing, right? Oh, say L'Hopital's rule, type 0 over 0. Now we gotta differentiate. Thankfully, we just differentiate one at a time. So upstairs we got what? 1 over 1 plus x squared. Downstairs we got ourselves a cosine of x. Well, this isn't hard. Man. Dang it. I will eventually find a difficult problem for us. Let's see. There exist difficult L'Hopital's problems. I tell you that right now. I do not think this is one of them, right? Because we can plug in 0 already. We get 1 over what? Cosine of 0 times 1 plus 0. If you wanted me to summarize all of those limit laws we teach you in Calculus 1 in a nutshell, what do they say? They say if we're taking the limit of an expression and you can plug the limiting point into the expression, that's what the value of the limit is, right? This is the determinate case. It's the case where the expression is actually a continuous function at the limiting point. All of the tricky stuff is when this doesn't happen, right? Like I can't plug 0 into the initial expression because 0 over 0 is not defined. And yet, after I apply L'Hopital's rule, I can plug in 0. Cosine of 0 is 1, right? So the answer is just 1. Your question? Could you guys see how to make this limit work out to a half instead of 1? Check it out. If you just put a 2 right up here, like this, it's still type 0 over 0. When you differentiate, you get 2. You get 2x, right? And then what happens? So there you go. There is evidence, right? 0 over 0. I just showed you it could tend to 1. And by changing this, it could tend to 1/2, right? You could easily replace my 2 with like a p and show that it could tend to 1 over p, where p is arbitrary. This is why we say limits of the form 0 over 0 are indeterminate, because we don't know what they work out to until we work them out. They're indeterminate, yeah.
This is actually probably a really stupid question.
Probably not.
1 over 1 plus, it might be, 1 over 1 plus x squared divided by cosine of x. Why isn't that cosine of x over 1 plus x squared, which would also equal 1 when x goes to 0? Because, like, I thought cube change flow or something like that. I don't know. Maybe I don't know.
You thought, what?
Can you just explain how you got from 1 over 1 plus x squared over?
Oh, yeah, sure. So there's,
Isn't it cosine?
so here's the rules. If I've got a fraction over a fraction, then the way it works is the numerator of the, the denominator of the denominator is the numerator of the numerator. I mean, here's the letter game, like this. So b up here becomes b down there, right? This d flips upstairs. So I've got 1 over 1 plus x squared, which just brings the x squared down here. Another way to see it, 1 over 1 plus x squared divided by stuff. What's that mean? That means 1 over 1 plus x squared, yeah, times 1 over stuff, right? So that's why we just get this times what was there.
So I get the left and get the same answer.
Oh, maybe. Or unlucky. Let's see here. I'm not sure. Well, that was not as much trouble as I was hoping for. Let's see here. Let's see here. Eraser dust in my mouth. Disgusting. That looks unpleasant, maybe. You know what? I'm going to stop looking for unpleasant problems. We will find those. You bring them to me. We talk about them in a future class. I'm going to talk to you about the other kinds of L'Hopital's rule. So, indeterminate forms. What are the indeterminate forms that you got to watch out for? We've already seen 0 over 0, right? Infinity over infinity, right? These are indeterminate forms, right? What's another indeterminate form? Another one we saw already today, 0 times infinity, right? The one,
Infinity times infinity?
Infinity times infinity, just infinity. That was the one.
Infinity minus infinity.
There we go. This one we have not run into yet. I was trying to think of a good example of this. What's a good example of that one? Number 57, I think. I'll go with that. Limit as x approaches 2 from the right, I think it is, of, if I had 8 over x squared minus 4 minus 1 over x minus 2, I think. Oh, no, more exciting. X over x minus 2. Right. So if you think about, what does this 2 from the right mean? This means essentially that we can think of x as being equal to 2 plus some little epsilon, where epsilon is greater than 0. Like, that's what that limit means. We're considering values of x which are really close to 2 from the right, right? That means that you can look at x as being equal to 2 plus some little epsilon. So if you think about that, what happens if you plug in 2 plus some little epsilon into here? Well, you get 4's cancel and you're just left with like a little epsilon squared and a 2 epsilon, right? And here you're left with what? Just an epsilon. Yep.
What does epsilon mean?
I'm just using it as a variable. I'm just saying epsilon for a very little, a small constant. So, I mean, the limit, here we're at 2, right? So here's 2 plus epsilon. So we're thinking about getting closer and closer and closer to that point this way, right? So if I want to pick an arbitrary point close to 2, but on the right, just 2 plus epsilon does it for me. If I want to think about the limit in terms of that, I could. If I plug 2 plus epsilon into this, what do I get? I get, anyway, let me get to the point here. This is infinity, that's infinity, right? And this is type infinity minus infinity, is my point. Let me just humor me for a second here. If I plug this in to the limit, it's interesting to think about that. So you square that, what do you get? You get 4 plus 4 epsilon plus epsilon squared minus 4, right? Which is equal to 8 over 4 epsilon plus epsilon squared, right? On the other hand, if we look at x over x minus 2, that's going to be 2 plus epsilon over 2 plus epsilon minus 2, right? Which is 2 plus epsilon over epsilon. To me, these are sometimes helpful because I can look at these expressions and clearly see what the limiting behavior is, right? Like, what happens with this expression? I'm getting 8 over a very small positive quantity. So this is tending to infinity. In this, I'm getting 2 plus something tiny divided by something tiny. So this is also tending to infinity. So this algebra here shows me clearly that these two fractions are, in fact, tending to infinity and minus infinity because of the minus. That's all I'm doing with this blue algebra. Your instructor may or may not have ever shown you this way of thinking about it. Right? Because you can think about just plugging in you can think about plugging in like 2.01 into these expressions and seeing what happens, right? That's another way of getting at the same animal, right? Think about plugging in number close but not quite there, see what happens. Yep.
Professor told me that some infinities are bigger than others. What does that mean?
Some infinities are bigger than others? Well, that means like, I mean, all these are illustrations of that, right? Like apparently the e to the x is a bigger infinity than x. I mean, we could think of it. Yeah, these kinds of comments should be taken with a grain of salt. I'm not sure what they mean, but now this, how do you deal with infinity? Minus infinity? This is not actually L'Hopital's rule. What you got to do is, what do you think? Algebra, yeah.
Take the limit of each one.
Can't do that. We can't take the limit individually because there's, like the limit, we have the limit of f minus g is equal to the limit of f minus the limit of g assumes something. It assumes that the limit of f and the limit of g separately exist and are known to us. Here, both limit f and limit g are infinity, which means they don't exist, which means the limit laws do not apply. So I can't, if they did apply, I could just assume, oh, it's infinity minus infinity, it's 0. And it wouldn't be indeterminate. It would just be 0 every time, right? But it's not. So what do you guys, we do? I heard algebra. I'm going to go with that. So what algebra can we do? We got two fractions, right? Common denominator, right? So this is 8 minus x times what? X times what? You fill in the blank for me. I heard an x plus 2? All right. Very good. All right, now what do we got? Let me clean it up just a bit before I go forward. So x goes to 2 from the right of, what's that? That's minus x squared minus 2x plus 8 divided by x squared minus 4. Is that 0 over 0? Plug in 2, what happens? If we plug in 2 into the bottom, we get 4 minus 4, which is 0, right? If we plug 2 into the top, we get 4 minus 4, which is minus 8, plus 8, which is 0. So this is type 0 over 0. I can apply L'Hopital's rule. Of course, you could also factor, but let's do L'Hopital's rule because it's more fun. So we get minus 2x minus 2 divided by 2x. Now what do we got? If you plug in 2, we got, on the top, we've got minus 4 minus 2, which is minus 6, right? Minus 6 divided by 4, right? So what do you say, minus 2/3? I think that's right. Minus 6 over 4, a.k.a. minus 3/2, I guess. Yeah, that's okay. I've done worse today. Much worse, don't worry. I mean, I think yesterday I couldn't factor at the end of the day. Like I'm staring at like a simple quadratic. It's like m squared minus 2m plus 1. I couldn't see it as m minus 1 squared. It's like, so sad. So sad. Anyway, so there's infinity minus infinity. You complete the square. I mean, make a common denominator is usually helpful. And a lot of times after we make a common denominator, we'll find that we have to use L'Hopital's rule. You could have factored out, well, I don't know, maybe, shut up. Anyway, what are the other indeterminate forms? There are 3 others. There is 1 to the infinity, infinity to the 0, and I think, I forgot the other curses. There's one more. There's 7 of these. No? All right. I guess it'll remain a mystery for now.
It's not 0 to infinity, right?
I think it's 0 to the 0. Hey, I hauled this book to class. It ought to be worth something to me, right?
Yes, 0 to the 0, page 562.
562. If the book says it, it must be true. Very good. All right. Proof by book. I'll allow it. Okay, so let me show you the quintessential example of this. Would be something like this. Limit as x goes to infinity of 1 plus 1 over x to the x. The question is, how do you deal with something like this? All right? How do you calculate such a limit? This is indeterminate. See, because as x goes to infinity, what do we got? This is type 1. This goes to 1, right? And this is type 1 to the infinity. Okay. So your book might do it a different way, but here's how I'm going to do it. I like to look at this and say, aha, I'm going to look at this as the exponential of the natural log of the thing I'm limiting. Now, I can do this little trick, provided that the limited function is positive. This makes sense because 1 plus 1 over x to the x as x goes to infinity is positive. So I can take the log of it, and I can take the exponential of that, and log and exponential are inverse functions. This is just like doing nothing, right? Except it actually does something, because now I can rewrite this as the limit as x goes to infinity of the exponential of, x times the natural log of 1 plus 1 over x, right? Properties of logs. I can pull the x down. But there's something else we know. Where's the exponential continuous? Right. That is true. But also 0 to negative infinity. Good news, exponential is everywhere continuous. And continuous functions, you can pull limits inside the arguments of continuous functions. This is a theorem of limits. So I can say, well, aha, this is really the exponential of the limit as x goes to infinity of x times the log of 1 plus 1 over x. And then what I usually do at this point, because I get sick of writing exponential, is I give this thing a name. I make it famous. I call it star. There we go. And the question is, how do you calculate star? So I'll do that over here. So we're limit as x goes to infinity of x log of 1 plus 1 over x. Now, what can I do? This limit we face. Can you guys tell me what kind of limit is that? It's infinity times what? What's the log of 1? 0. This is infinity times 0, which is indeterminate, but I can't yet use L'Hopital's rule, right? So what we're going to do is we're going to move the x downstairs. So we've got the log of 1 plus 1 over x divided by 1 over x. See, x upstairs is 1 over x downstairs. Yeah.
I'm a little confused. Is what you did, you raised that function to e, and then you pulled down your x?
I took the whole thing and fed it. I mean, I'm using this identity that basically theta is equal to e to the natural log of theta for theta greater than 0. But theta is the expression that we're limiting at. Now, the reason I did this is what? Now, as x goes to infinity, what happens upstairs? It goes to 0. Happens downstairs, goes to 0. So by L'Hopital's rule, type 0 over 0, we've got what? We get 1 over 1 plus 1 over x times minus 1 over x squared by the chain rule, divided by minus 1 over x squared, right? The minus 1 over x squareds cancel, and we're just left with the limit as x goes to infinity, 1 over 1 plus 1 over x, which is what? It's just 1. Don't worry, we're almost done. This, well, yeah, it's just 1. This goes to 0, right? Which means the whole thing goes to 1. So star is equal to 1. So I go back, I plug in star. This is equal to e to the 1. What would happen if you replaced x with like x times, what if I replaced x with like x times b? What if I put a b up here? What would it do? If I put a b up there, where would it track to in this calculation? Come on. Man, it's really stuck on there. B. 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 So this limit defines the exponential function with argument b. This formula comes up in the study of compounding interest. It's another way people discovered the exponential function in terms of compounding interest. But anyway, for us, it's our first and most important example of a type 1 to the infinity limit. Okay. We'll do more of these next time, and then we'll, not the whole time though. Hopefully next time I'll do like maybe 10 more minutes on this, and then we'll go on to improper integration. We got to get back on track somehow or another, since we've taken so many days off for silly things. No, my grandma's funeral was not a silly thing. I take that back. But for some important things and some unnecessary gloating that other day. But anyway. Oh, I had you guys watch a video anyway. We didn't get behind, did we? No? Oh, I'm supposed to give you something, right? Yeah. Let me do that.